So hi everyone, we are the AI Guide Dog team, and today we will be presenting our progress over the course of this semester. So just to give a high-level overview of what our project is, our goal is to use sensor and video data from iPhones to provide high-level and fine-grained directions to help the blind and visually impaired. And the reason that this is important is because people who are blind can currently use Google Maps for directions, but Google Maps does not provide a high level of granularity when it comes to location and then also for fine-grained directions. So there's a lot of error and margin of error when it comes to their GPS data. And currently, blind people and visually impaired people are able to get around this by using guide dogs. But the problem is guide dogs are difficult to train and have a limited lifespan. And they also create an additional overhead for the blind person to maintain and care for the animal. So our project is to basically build an AI guide dog application that can help sort of create more fine-grained, create higher resolution data to help guide the visually impaired. So a previous iteration of this Capstone project had already built a data collection pipeline for collecting sensory data for model training. And for this year, we're trying to build upon that pipeline and build an entire model that goes from data collection to model building to an actual AI guide dog mobile application. So the general problem description can be divided into two main problems. The first problem is creating an end-to-end pipeline for egocentric trajectory prediction. So this will cover having a data collection module, performing data preprocessing, and then doing prediction and explanations. And then the second problem that we want to tackle is to improve upon the existing app design and make it much more user-friendly and able so that people can use it to collect data for our mobile application. So again, our proposed solution can also be divided into two main categories, so data engineering and model building. So in the data engineering part, we have three main components. So that will be labeling, transforming the data, and balancing it. So for labeling, we basically plan to use compass data from the iPhone. So we plan to have people collect data in very controlled environments like a grocery store or a library where there's a lot of opportunities for turns and a lot of opportunities for short turns. And we'll have an automatic labeler that uses compass data from the iPhone since we won't have access to GPS indoors. And then we'll have a transformation module, which will transform the data into a format that's usable for module to balance out the data. So we have an equal number of labeled data. And then we also will have a model building sort of section in the experimentation pipeline, which will basically be taking all of these features and inputs, so video, GPS, accelerometer, optical flow, and compass data, and we'll be leveraging both multimodal and unimodal models to sort of build a more fine-grained egocentric prediction module, hopefully by the end of the semester. And then we also have a model explainer and model replayer at the end of our whole pipeline.
So here are our two main hypotheses. First, we hypothesize that egocentric navigation is possible with image snapshots and sensor data. We have reason to believe this hypothesis as existing works have shown that trajectory prediction is possible using video data. And in order to validate this hypothesis, our approach is just to simplify the task, execute, and iterate through it. Second, we hypothesize that accurate visual explanations can be generated from model predictions. And we believe in this hypothesis due to existing work such as GradCam, which is able to provide interpretability to standard image prediction tasks. At a high level, our project involves working on four major features. First, we have an experimentation pipeline. This is in order to build models and validate various hypotheses that we have for this project. Second, we have a trained model. So this is the ideal best performing model that we hope to obtain during this Capstone project that will be deployed on the app, which is our third major feature, to make predictions and guide the visually impaired. And finally, we have a collected annotated data set, which will be open sourced in order to help researchers and enable more adoption for further research in this area. The figure in the right shows the data collection process. So overall, as we can see here, data flows into the model through two major sources, that is camera and various mobile sensors. We'll be going into the depths of each of these modules in the future slides. So here is a short demo video for the expected outcome from the app. This clip was taken from navigating in the CMU library. So the app would take in two kinds of data, that is video and sensor in real time, and output real-time timely predictions. And these predictions would be made in three labels, as we can see here, which is turn left, turn right, or move forward.
The primary stakeholder of our project is the blind community. The system will be deployed as an application that can be installed and used on an Apple iPhone 11 Pro. And for an example use case, we have a blind user that wants to go from one point to another. He or she will be carrying the iPhone with the camera facing forward and set the destination on the phone. The application will then take in image and sensor data and output navigation instructions to the blind user in real time. For this use case, our application will have to be sufficiently accurate and operate with low latency. The application also has to cater specifically for blind users to ensure a good user experience. Also, we will eventually be releasing this egocentric navigation dataset to the open source community. And for this, the intended users will be researchers in the computer vision community. This will serve as a new benchmark for egocentric trajectory prediction and navigation. And as such, the document has to be well documented and easy to use. Sorry, the data set has to be well documented and easy to use. So coming to our system functionality, we have four major components. Firstly, the open source data set that we have collected in a controlled environment. This contains raw videos and sensor data. And this is then processed and labeled in some of our modules. We will also be releasing mobile application, which will also be used to collect data about, sorry, I can't see the slide. Yeah, it'll be used to collect adversarial examples through the app. Yeah. So diving deep into the experimentation pipeline, the first module that we have is the data transformer module. This takes in raw video and sensor data, and some of the configurable parameters for this module are segment length of the video and frame rate. And this module pre-processes the video segments and gives it to the data labeler. This module labels the data for every frame in the video as either left, right, or forward. And then the output from this module are passed to the data selector, which balances data for training, validation, and testing. This data is passed on to the augmenter, which augments the training data set. We'll be talking more about this in further slides, but some of the techniques that we used were flipping frames and rotating the frames. We also have the main train test module, which makes the predictions, and some of the models that we experimented with include CNNs and Cornwell STM. Finally, we also have an explainer module, which provides explanations into the predictions, and in the video frame, the regions that are more significant for making the predictions are marked by this module. And the last module that we have is the replayer, which overlays predictions and saliency maps over the videos and serves as a demo for the MVP.
So these are the non-functional requirements for our project. To briefly go over them, availability is just that our application is available in two forms. The first is the experimentation pipeline, where we can tune our hyperparameters and build a better model. And the other functionality, non-functional requirement of availability is that we have an application that the clients, or for which is the blind community, can use. In terms of security, it's just that our data is protected and making sure that our data doesn't leak to other people. Testability simply just means that our application is testable and our model is testable, so that we can make sure that there's no kind of errors or major errors within our pipeline. In terms of interoperability, it's just that both the application and the pipeline, the experimentation pipeline, can communicate with each other nicely and correctly and smoothly. In terms of scalability, we're just making sure that as the number of users, which is the blind community, increases, our application and our model can handle that. In terms of performance, we are making sure that our model can predict fast enough that it doesn't kind of hinder the user experience when you try to make a turn. The turn predicts in time. In terms of usability, it's just making sure that our UI is easy to use, especially for the blind community. And lastly, observability is just we're making sure that we can kind of monitor all the resources, for example, using AWS CloudWatch in the future. For resource requirements, there's two main resource requirements, data requirement and hardware requirement. For data requirement, we require that the data comes in as two main formats, MP4 for the video and CSV for the sensor data, such as accelerometer, gyrometer, GPS, and compass, and so on. Moreover, we may use additional kind of open source data sets in the future if it deems necessary, if our data set that we collected in-house is not enough. And for hardware requirements, we require that iPhone 11 or later, because these iPhones have the wide angle camera that we ideally want to use. But generally, we use iPhone 13 for this. And in the future, we might use some AWS resource to deploy, which we will talk further later in the presentation. Whoa. Okay, for design consideration, there's three main things: assumptions, constraint, and system environment. For the design consideration for assumption, we are assuming two main things. Again, the data comes in as MP4 and CSV format, and also that the labels are generated correctly. And this is currently true or valid because we collect all our data in-house, and we can make sure that, for example, the speed of the person is walking correctly, the turns are turned correctly. In terms of constraint, there's three main constraints. The first constraint is that when we walk, the phone actually moves up and down, and that's the variance in the z-axis that we have to take into account. Secondly, different types of phones have different sensor accuracy and different kind of camera angles. So we have to make sure that our model kind of accounts for this. And lastly, people walk at different speeds, and this can cause a lot of variance in our prediction. And we have to consider this constraint in the design consideration. Lastly, for system environment, we basically want to consider that we want to deploy this model in the future on AWS, which we'll touch on later. And also that we want to deploy currently solely on the iOS smartphone.
Coming to the system architecture, so this is how all the modules that Aditi talked about previously come together. So the experiment configurator sets the configuration for the experiment, as the name says, and the raw data itself is stored in the cloud storage, and it's pulled by the data labeler and transformer, and it goes through this pipeline, and the outputs come on the replayer module. So as you can see, all the rectangles here are representing each of the submodules that we have in our pipeline. The cloud storage and data collection app, they were created by the previous year's Capstone team, and we are we're building over that. And yeah, each of these submodules, apart from these two, have their individual subtasks and milestone targets and requirements, functional and non-functional. So coming to data design, our videos are stored as MP4 and sensor data as CSV. So the data transformer pre-processes them into a NumPy array format, and the model trainer takes the NumPy array input and outputs the best performing model as a .pth file, which we will be using in the iOS application later to make predictions.
We now go over the ML models that we used for our prediction task. Essentially, our problem can be modified, put up forth as a time series prediction problem, where for every frame, we predict a label which is to take a turn either left, right, or go straight in the next 1 second. We experimented with multiple models this semester. So the last year Capstone team had conducted a POC based on the time distributed CNNs. This semester we experimented with RNNs, Conval STMs, and CNNs. Out of all these models, we found that CNNs and Conval STMs to be most promising. Hence, we'll be describing these two architectures over here. For the CNN, we fine-tuned the famous ResNet 18 on our egocentric walking data set. And we essentially modeled it as a classification task with 3 labels. CNNs only consider point-in-time information, and they take each frame features independently and make predictions without any consideration of the context or the past history of the video. For the next model, which is ConvLSTM, it is a type of recurrent neural network which is mainly used for spatiotemporal prediction on videos. This, as seen from the figure here, this has the similar architecture and mechanisms as your regular LSTM model, but instead of all the operations on the LSTMs, we use convolutions on the state-to-state and input-to-state transformations. In this, predictions are informed by the time series history of the preceding frames, and it kind of helps us to add context in order to predict the next frame. This model is also better suited to adapt to our stage 2 goal of using high-level a priori signals in our predictions that can better inform the future decisions to take. For the stage 2, we are currently in pipeline and experimenting with certain high-level inputs for our architecture apart from the video signals. So this mimics our end goal of navigating in the real world, where the user will input a destination and he will be guided by high-level GPS signals. So we aim to incorporate such GPS signals into our model predictions. In order to simulate this scenario, we introduce high-level GPS signals 4 to 5 seconds before the actual turn. And we again use the ConvLSTM models to encode this context and also take the video predictions. And the actual predictions will be output 1 second before the turn, depending on the walking speed of the person and the egocentric video signals. To evaluate our models, we use the cross entropy loss, and to further test them, we use confusion matrix, F1 score, and accuracy metrics. We will also be performing online evaluation of the model, whereby depending on the statistics collected, we will note each data point where the user actions deviate from the model predictions, and we will use this to further train and refine our model for improving its prediction accuracy. This is our end proposed deployment model. So here we use a mobile application in order to take the video, egocentric video, and the sensors. These will be processed and inputted into the model in order to get the navigation results. Apart from that, we will also be using external APIs such as Google Maps in order to use location data. On the backend, we'll continuously be collecting more data and storing it in the S3 bucket and continuously evaluate and refine the model, train it. And once we achieve significant improvement, we will again deploy and update the model, which is deployed on the user app. We will also be monitoring our model using Amazon CloudWatch.
So I'll be talking about some of the results that we have achieved till now. So the first thing that we did was to reproduce the baseline model that was used by last year's Capstone team. So this was the time distributed CNN model. We recreated this in our own pipeline using PyTorch. We also tried it with two of the labeling methods, optical flow and compass. These were also proposed by last year's Capstone team. So these results are, we have two kinds of data, outdoor data and indoor data. So these results that I'm showing right now are for the outdoor video data. The baseline models did not have a very high accuracy. For optical flow labeling method, the accuracy was about 0.62, and for compass it was 0.47. Then we tried out a simple LSTM model using the optical flow labeling method, and we got an accuracy of about 0.55 with that. Then we added some data augmentations to this model, but that did not really help us improve the accuracy much. After this, we tried our ConvLSTM model using the compass data for this outdoor video data, and this model is the one that performed best, so it gave us an accuracy of 0.82. For the rest of our pipeline, we are using this model, and we're also expanding upon this. Now after this, we have some of the results for the indoor video data that we collected this semester. we have two kinds of models here, as Aishwarya described previously, the CNN model and the Cornwell STM model. So the CNN model is a much simpler model. The Cornwell STM model takes into account the history as well. As you can see, the accuracy for the Cornwell STM model is 0.85, which is much better than the CNN model, which is only 0.77. This is to be expected since the Cornwell STM model takes into account the history as well, but the CNN model does not. It only takes one frame into account. However, a thing to note here is that our data is highly imbalanced. The problem is that the front label occurs much more than the left and right labels. As we observe from the results, this causes a skew in our data set and highly biases the result. The models learn the characteristics of the front labels much better than the left or right labels. This is contrary to what we desire. We require our models learn turns very well. Therefore, informed by this peculiarity of our data, we assign more weights to the left and right labels during the training of the models. As a result, the models did quite a good job learning these labels. Furthermore, for both the models, we also observed that there is a lag in the time series of the predicted labels as compared to the actual labels. This means that the models are not able to make a turn prediction much ahead into the future. This effect is less pronounced in the Cornwell STM model, given the fact that it takes into account the history as well, and it is more pronounced for the CNN model. Yeah, we also, after this, we also tried some data augmentation techniques and some data transforms to see if that helps our model generalize better. So we added some data transforms such as color jitter, hue saturation, horizontal flipping accompanied by flipping of the label, slide rotations to ensure that if the phone is slightly tilted, the model is able to generalize well to such kinds of situations. We got some improvement for the baseline model for time distributed CNN. However, for our two main models, CNN and Cornwell STM, we got very slight improvements for data augmentation. However, this is a good insight to have because we kind of understand that we need to train our models on more data now.
Yeah. So to provide interpretability to our models, we decided to apply the GradCam explainer module to our trained models. So this slide, we can see the explainer module applied to the Cornwell STM stage 1 model. And on the left, we have a video of stage saliency maps, which shows the importance regions of where the model places its focus. So as we can see, the model is focusing, like the red regions are the regions of high importance. So as we can see, the model is focusing on the road and the surrounding regions. And in particular for the road, we can see that the model is looking at the segment of the road a few meters ahead. So this makes sense because that's the most important area when the model decides whether it needs to make a turn or if it's going straight or whatnot. So for the video on the right, we actually prepared a demo video to explain to others how and why our model makes its prediction. So as we can see, yeah, so we included the saliency maps, the sensor data, and whatnot. Yeah. So for the CNN model, we did the same thing. And this is the stage video. Yep. So as you can see, the video is, the saliency maps are very sparse in nature in terms of the importance regions. So this might mean that the model is overfitting on the training data, where it simply predicts straight most of the time. However, on the other hand, in the maps where with the regions present, we see that the model tends to be focusing on the right regions, as can be seen in the figures on the slide. So this slide, we see some of the risks that our project faces. So for the first type of risk, we have business risk, whereby even in the case where our app is deployed, there is a lack of user demand. So we can address this by improving our user experience through user feedback. Secondly, we can also, there's also product risk, whereby in the case of a model misprediction, we might cause users inconvenience, or we might even cause worse off injury. Furthermore, when our app is down due to technical issues, we might cause huge inconvenience to users. Lastly, for our project risk, we might require more computational resources than required, and we also make a huge assumption that iPhone can run the model inference real-time with a sufficient frame per second to enable real-time usage. So this slide, we can see all our tools. So our model experimentation mainly uses Python, and yeah.
So to make sure we can finish everything on time and at a proper pace, so we just break down everything into 5 stages, 3 for this semester and 2 for the next semester. So for this semester, we finished the data acquisition, design and putting up the pipeline. And for next step, we will be collecting more data and retrain the model, and also developing the AI Get Dog app. And here are the breakdowns of the subtasks needed to meet these milestones. So the ones highlighted in green are what we already finished. And for next step, we will be collecting more data through the AI Get Dog app and adapt the model to the newly labeled larger data set, and also make the model multimodal manner, and also trying to formulate the problem to a regression task, and also change the sequence to sequence classification to a sequence to one classification task. And looking back to what we did this semester, we worked in sub-teams and did weekly meetings with the mentors to do the brainstorm about pros and cons of the design decisions. And also the methodology and the results are well documented. And in general, we finished the work expected. Yeah. So here's, that's all for our presentation today. So thank you. Any questions?
Thanks, guys. I think the slide template also included references and terminology definitions and stuff. So please make sure you add that for your final presentation, because we don't. Okay, good. So you have that stuff in there. Great.
Also have some humor.
So I think it would be great if the next time you present this, you explicitly talk about the sub-team structure and what each person in the team is assigned to. There's lots of students on this project, and there's lots of work to be done, and you guys are making good progress. But I don't have much visibility into sort of who's doing what. So make sure that you, add a slide like that when you present again in the fall. Not a big deal, but it will improve the quality of the presentation. So the non-functional requirements slide that only had icons on it, that's not a standalone slide. If you give me your slide deck, I have to guess what the icons mean. So even though that's a fast way, to put together a slide that reminds you what to talk about, it's not a very useful slide for your audience. So probably for the final, you want to have real, text bullet items there. Again, a minor point, because you did go over most of the non-functional requirements in detail. One thing that I don't think I heard you mention, though, is safety. So what I'm wondering is, if I'm going to put an app in the app store that non-sighted people are using to walk around in the real world, what kind of safety guarantees do I have to provide, or is there no policy regarding apps like this? So have you guys thought about that, or is that something that will happen, once this is ready to leave the laboratory and go into the real world?
So currently we have not done real-time testing on this. So we ourselves are not, we don't have enough data to tell how safe it is to use, and we are assuming that at this stage, it's not safe enough for real-time use.
Okay.
So eventually, when we test it on real-time data, we will get back to you saying that, okay, this
Great.
is.
Yeah, so it might be good to sort of talk about which ones you're focusing on for this capstone versus what is obviously, a requirement for the future, so that, naysayers won't think that you've glossed this over, but that you're just focusing on the most important stuff first, right? Related to that, there's always a concern, when you're running heavyweight stuff on somebody's mobile device, that you're burning up their battery. So you guys measuring power consumption at all here? Because when you start turning on, Google Maps and GPS and the camera, if somebody has an older phone with a weak battery, you might drain it pretty quickly.
Yeah, that's something we have in pipeline for our next semester, that we are focusing on the iOS app itself. We are not focused on the app itself this semester. So when we do that, we'll probably be doing the battery testing and also how much heat it generates, so that we know how well our model is performing on it.
Yeah, again, not something I'm expecting you to address in this capstone, but you should show awareness of it. To show that your thinking goes, all the way to the real world, even if your work is only going to be sort of the first step, right? Okay. Oh, I noticed that in the hints that were being generated by the model, there were no distance hints. So it didn't say turn left in 3 feet. And then you kind of mentioned that what you're trying to do is sort of have the direction be kind of, 1 second in the future. But then you also mentioned that it kind of depends on how fast or slow somebody is walking, right? So if I think about that, and I'm thinking about writing a user manual for this, or like some training guides for this, I would probably want to say something like AI Guide Dog always notifies you 3 steps in advance, because that would be easy for people to kind of train on. It may be that most people are walking with a cane, so it doesn't matter. You just need to tell them what direction, and then they're going to tap it out and then make the turn just fine, and they don't want the distance. But I felt that was, kind of a little bit fuzzy. It might be cool to be able to figure out from motion, what somebody's cadence is and sort of how many steps and so on. But if everybody's using a cane anyway, that's like overkill and maybe an unwanted complexity. I see Anirudh nodding his head there.
That's one of the reasons we're predicting it like 1 second before, so that the variance, depending on the speed, is less. Even though one person is walking faster, one is walking slower.
Right. Okay. So then I saw something interesting on the results. It looked like there was a flip-flop on the best model between CNNs and Conv LSTMs on the front facing data. And I was wondering whether that was due to data skew. Is it because there was enough data for the CNN to somehow surpass the Conv LSTM?
Yeah, so for the CNN, we see that the front labels have a much better prediction, but our main goal is actually that we have better predictions on the turns, like the right and left, which the Conv LSTM model is better able to, generalize to that.
Okay.
Because predicting front label is quite easy, because that data for front is much more and much varied for the front labels. So predicting front is much easy, which CNN is able to accomplish easily. But the harder part.
So what do you think? Do you want to have like a weighted average or something as the real metric?
Yeah. So for training Conv LSTMs, for training CNNs also, we did use weighted average, but somehow for CNNs, the front labels turned out, again, dominating the model prediction. But
so I find it really interesting that you guys are already kind of intuiting that there's a metric that has to do with what's important. And I think it would be great for you to basically define that metric and then show that, Conv LSTM always, is better there. I don't know whether it's an average or a weighted average or, what the right thing is there. But if that's your explanation, you need to be a lot more proactive about that the next time you do the presentation, so that I'm not left wondering why, you were claiming that Conv LSTM was better when I saw that number kind of sticking out there.
Yeah, sure.
Okay, let's see if I had any other questions here. That's it. I'm impressed. I think that you guys got a lot of work done this semester. You do have a lot of students in the team, so if you didn't have a lot of results, I'd be kind of worried. I think most of the feedback is not really on the science side. It's more on how to do a good presentation. You will do a presentation in the first week of the fall, which will be the revised plan, and try to incorporate this feedback into that. Especially, I'm going to want to see who's working on what throughout the fall. I think your fall plan is kind of reasonable. But there's not as much detail maybe in there as you had in your spring plan, which is actually to be anticipated at this time. But I think if you have just as detailed a plan for the fall and then follow up with the same team process that you've been following, you're going to be great. Okay, any questions from the mentor or the TAs?
I have a question about the non-functional requirements. So, for example, there was a requirement called performance, and you would preferably want to be more specific as to what that means. I think you said something like it should be fast enough for the user. So fast enough is ambiguous. You have to give a number, right? Something has to work in 300 milliseconds. For example, if you're putting safety as a non-functional requirement, it should have a particular standard that you're going to follow, or a particular test set that you're going to follow, and so on. So it has to be a lot less ambiguous when you're declaring them. Also, are all 8 of them non-functional requirements that you need? Are there going to be some that you will prioritize above the others? So that's something you might have to think about, because there will be work that goes into each of them, and you might not have the time or the resources to work on all of them, and you might have to have a priority plan ready for which one is going to be prioritized. Also, good job on using Microsoft project planning for making the milestones.
Yeah, I think having a slide where you talk about the non-functional requirements in general, and then what we will cover in this capstone as a second slide is exactly the way to address this comment, because then you'll show that you have the right awareness, even though that you really don't have the scope to address them all.
Yeah.
Great. Anirudh, what do you think? Where does this team need to improve?
I mean, they have been doing better than what I expected, especially when the team gets larger. They have basically gone and divided the people between who comes early in the pipeline to who comes later. And as the things early in the, because it's kind of like flowing from start to end, folks have been meticulous that even if they don't have the data, they have fake APIs, they have fake data to pass, and so the modules can be built in surprisingly quick time. So, and finally, as things started to mature at the top, people started helping, people who are downstream. The place where there is potential for improvement, actually, which was, which happens with large team dynamics, is how to develop the module so that everybody can continue using it. So obviously people hack and prototype first, but then they quickly started to get the cadence of, no, we need to develop it in a more systematic manner, and they did that. So that was kind of good. They identified that it will go towards a mobile application. We'll have to go towards low power, but for now, just focus on how do we prove this even works.
Right.
And to end it, I'll just say the thing that I found the most exciting, because I meet them like every week, keep talking to them. The slide number, there's a slide with the video, the very first slide, if you can move it there. No, the where you actually move. Like the real results, not the.
I think the interpretability part.
Yeah, like, yeah, just play both videos. I mean, the fact that this works is amazing. The fact that this works, this is not like you can just use easy GradCam and get it to work. It required like getting deeper into the model and then trying to, you see this this green thing which goes which direction it's going out. I mean, that's impressive. I was surprised, by the way, and I know this project very closely.
Yeah, well, I think the basically, understanding the data, understanding the given code, and then getting a plausible new release candidate that improves significantly on the state of the art is like the trifecta of the first semester, and I think these guys did that very well. So I'm looking forward to more in the fall.
And they were able to raise requirements. So Tawfiq, who's on the call, who was developing the app, they were able to raise that, hey, we need a wide angle camera, because in many of these cases, like a small degree of view is not great enough. So I'm happy with the team.
Great.
They're amazing.
All right, guys, thanks. Great job.